Hello, my dear students. Today I am going to present before you a topic, atomic view of dielectrics. Already we have studied about the conductors. In the conductors, a question of electrons are freely available, so they can conduct electricity. Whereas in the dielectrics, if you see, these electrons very much bound to the nucleus. Therefore, they almost don't conduct electricity through them at ordinary electric fields. These dielectrics have so many applications. If I ask you, refer back your lower class study, their teachers might have told you these dielectrics, when they are kept in between the capacitor plates, their capacity is going to increase. That you might be knowing. Now, before we go for the detail of their applications, I would like to present before you their classification. The classification says that there are two types, non-polar dielectrics and polar dielectrics. Now, let me go for first of all a polar molecule. Now see, this polar molecule is having number of atoms. Everybody knows. And each atom will have positive negative charges. Positive core is like a nucleus and negative is electrons. Now for a molecule, if you see, all these positive charges together will have their own center of gravity, and negative charges will have their own another center of gravity. These two center of gravities in a polar molecule are not coincided way exist. Whereas if you go for non-polar molecule, now look at the non-polar molecule. In a non-polar molecule, these positive and negative center of gravities are very much coincided. Almost one over the other will come. They coincide together, will exist. Now, look at these examples of your polar and non-polar molecules. This information says you very clearly. In a polar molecule, examples are like water and acetone, etc. are present. Whereas for the non-polar molecule, carbon dioxide, H2, N2, O2, etc. are present. Now let me take a non-polar molecule, one example as carbon dioxide. And this carbon dioxide, if you see that molecule, it will have almost 180 degrees bond angle. Look at the diagram. Between C and O, one bond, double bond, and another double bond on the right hand side, CO is there. And they are like linearly placed. And the diagram also says that this is like a symmetrical molecule. And for the symmetrical molecule, further if you look at that, the dipole moment factors, small p, on left hand side and right hand side of the molecule can be visualized. The resultant of them, if we calculate by vector knowledge, we can get the value as 0. So this is all about non-polar molecule. Similarly, let me take a polar molecule, water, that is H2O, very common molecule. And this common molecule H2O, if you see, there is a bond angle, and that bond angle separation of OH and OH can be visualized with respect to O. And this particular molecule says that this molecule is like an unsymmetrical one. And the dipole moment factors here also, once again, if we calculate, they are spreaded like at an angle. Therefore, one can calculate the resultant value of this dipole moment of this molecule is a finite value using your vector algebra parallelogram law, and it is like a finite value. Now, let me speak before you how the electric field is affecting our dielectric substance, especially a nonpolar dielectric. Let us take a capacitor. Upper plate of it is positive charge, lower plate is negative charge. And in between the parallel plates, let us keep a dielectric slab of nonpolar nature. Immediately, induced positive charge and induced negative charges are going to be accumulated on this slab as shown there. Now, the electric field value that was applied between the plates, if you see, it is E0, whereas between the induced charges negative and positive, there is a field E dash. Hence, a resultant electric field E can be calculated using the formula E0 minus E dash. So it says that whenever a nonpolar dielectric is kept in between the parallel plates or applied with electric field, the electric field strength is going to decrease. Now let us study about electric field application on polar molecule. When there is no electric field applied on the polar molecule, these molecular magnets or dipoles, they are going to orient in different directions, so that the net value is found to be a very feeble value like small p. By the application of the electric field on the same polar molecule, we can see all these molecular magnets or the dipoles are going to orient in the direction of the applied electric field. Thereby, their dipole moment little bit seems to be increased, like P plus dP. The conclusions at a glance. Polar and non-polar can be distinguished in the following way. In a polar, positive negative charges center of gravity do not coincide, whereas in non-polar, they will coincide. In a polar, we can see the molecules are unsymmetrical molecules, whereas non-polar, they are symmetrical molecules. For a polar molecule, dipole moment is always said to be a finite value, whereas for non-polar molecule, it is 0. In the polar molecule, we can see in the electric field, the dipole moment of a polar molecule increases, whereas in non-polar, it is not so. Thank you, my dear students. Today, we could able to go for atomic view of dielectrics. Tomorrow, we will go for their applications in different fields also.